Next, we have Dr. Mahesh Maskey, who's a postdoc on the USDA ARF side. And he's actually under me. So we're gonna let him go ahead. He's going to present this talk at the National Sedimentation and Hydrologic Modeling Conference next week in St. Louis. So any feedback is welcome.
Welcome and thank you all for attending this my research seminar, virtually or in person. My sincere thanks go to Dr. Nelson and Dr. Professor Wilson, including INCAT seminar series team, for giving me this opportunity to talk about my research at sustainable water management. Research unit of the USDA. Today, my talk is entitled Simplified Framework to Calibrate Agrohydrological Model Hydrological Apex Model and Uncertainty Analysis of Runoff Parameters under Grading Operations. How it works?
No, it doesn't have an on-off button. I had it this way, but.
Working with you, what we do, right?
Yeah, we're
Trying the USB plug.
Yeah, did I bump the?
Maybe I can do it.
No, the whole thing.
Oh, we killed it. Nice.
Frozen. I think it's this.
Awesome.
Are you broadcasting it from online?
No. Anyway, okay.
Where is that?
It doesn't like hide video control.
I'm hoping with increased agricultural productivity for food security and ongoing climate change, we should try to regenerate sustainable ecosystem services by properly managing agriculture activity in small scale watershed. Small scale watershed, there are very few research have done in quantifying the water quantity and quality in small scale watershed under grading activities. Because grazing activity is one of the agricultural activity, and then especially they have very few literature in presented with hydrological modeling. So the development of the calibration of agrohydrological model was defined to improve hydrology related tasks such as uncertainty analysis. The reason is that existing parameterization mostly rely on the uncertain analysis, uncertain and unfamiliar parameter distribution or probability distribution of hydrological parameters. And the objective of this talk are to calibrate recently modified agrohydrological apex model with grading model in investigating response of grading operation and to runoff at the outlet of grassland and cropland via simplified procedure, and to utilize the simulated parameters within the prescribed criteria to perform uncertainty analysis in elucidating the range of sensitive parameters and response variables. Among 8 watersheds, we tested our protocol into small watersheds, WRE1 with grassland, WRE1 grassland with native priority, and WRE8 cropland with winter wheat and 1 year of wheat. Within the water resource erosion water WRE watersheds of the USDA ARS grazing lands research laboratory. Laboratory near Illinois, Oklahoma. The laboratory had been handling several research questions since its establishment. This study considered agricultural policy environmental extender apex as an agrohydrological model, which has its own database, including crop characteristics, fertilizer, tillage, and pesticide. Past researchers have demonstrated several applications in farm and small scale watershed, watershed analysis, but limited work that use the previous parent of the model in studying the impact of grazing operation in farm scale hydrology. Recently, Gilbert work et al. Added grazing model to the model with additional grazing database. The model is named with Apex grades. In this modeling task, the watersheds were delimited with using nitrogen tracking tool, which allows us to extract soil data and lineage data into Apex readable format, and some parameters from that file were updated or edited before using Apex grade editor spreadsheet. Nelson et al. Compiled and presented management data for each farm. They include planting, fertilizer, pesticide, grazing, runoff, and sediment data. And the grazing tables developed here are almost similar to the one suggested by Gilbert work et al. 2017. This study adopted weather data, precipitation, and temperature gathered from measurement for 1977 to 2018. Finally, two scenarios were developed: without and with grazing operations. In fact, this study concentrated on the study of on impact of grazing operation on runoff and sediment deposits at farm scale. So there are only 20 parameters related to runoff and sediment were chosen for a calibration purpose. They are nitrogen fixation, against the equation coefficient and exponent, sediment routing exponent and coefficient, rainfall interception, and soil erosion related coefficient, and etc. After setting up the model input and database suitable to Apex grid, a simulation period was defined. And this study considered performance metrics, max of efficiency, coefficient of determination, and percent bias as performance metrics. The one objective function used by Monk 2016 was reformulated, incorporating all these three matrices into one single expression. And this modeling task begins with improving the calibration method. As I mentioned earlier, this we are adding normal distribution of parameter space. And the calibration method is 5-step procedure. Parameter space generation is a discretization of individual parameters within the lower and upper limits of each parameter. They are derived from literature and the user manuals available. Then we iterated the model by picking up each parameter in a combinatory selection and save them. Then we evaluated the matrices of each iteration and store them for lateral use. Then we set the subset of parameters parameters that are within the morality criteria was chosen before selecting the base parameter set. The base parameter set was chosen with the set having minimum or maximum metric value, depending on which choose the matrix. The parameter sets within the morality criteria were used for certain uncertainty analysis. Since running the model many times is computationally expensive, so we sought help from high performance computing facility via USDA Signet to even for 100,000 simulations. This shows, this slide shows the protocol for the first slide here shows the protocol for uncertainty analysis that relies on calibrated parameters set with the adopted with the monastic criteria, and then we can mean and standard deviation of these parameters were calculated, and then we treat the model within mean plus minus three times standard deviation. And we ensure that these parameters should not be on the upper and lower limits of parameters. Here are runoff representations at daily scale from WRE1. WRE1, the x-axis is the date, daily dates from from January 1982 to 83 to September 2000. As in all the representations are equally comparable, despite there are some discrepancies in texture. Interestingly, the objective function value related to coefficient of determination and non-circuit efficiency in gauge data are almost similar. That means it had same set of parameters in both cases. They overlap. However, and in as other all the six meet the morality criteria as R square, which is coefficient of determination greater than 0.6, non-circuit efficiency less than 0.5, Py per absolute percent value less than or equal to 15%. And this multiple solution says that there is non-unique solution for hydrological processes or runoff process. As expected, and the runoff representation at daily scale in WRE are also equally comparable. Once again, x-axis is the time scale, time daily scale from January 1982 to September 2000. 2000 here, if you look the coefficient of determination and non-circuit, they are within the morality criteria, but not the percent bias, which is more than given the criteria. So we have to say 35%, not 15%. Here are the fundamental water balance components in both sides, both fields from at the monthly level. As seen, evapotranspiration is increased in the WRE1, runoff and deep percolation decrease also decrease. But in WRE8, the behaviors are almost similar without grading operations. But some changes appear occurs only after 1997. This is because the WRE8 has less infrequent grading and the similar application of fertilizer, pesticides, and other activities. And in general, if you look at graph, the more variability in water balance component between two scenarios in WRE1 are more variable than in WRE8. Here are the key component, key response variable from the model during the model from the simulation, and then from the simulation here, and please note that red both negative numerical value refers to the increased response variable after grading operation. As in WRE1, water yield and deep percolation decrease, but in WRE8, water yield is slightly increased, but deep percolation is decreased. So increase and sediment, soil erosion, nutrients like phosphorus and nitrogen, decrease in both cases. Again, both farms, so the evapotranspiration, drop biomass, drop forage or drop yield, and the for temperature state. Now we move to uncertainty analysis. These are monthly time series of runoff from both side from both field without and with grazing operations. Operation within the set within the represented by the parameter set within the monastic criteria that is simulated within the range mu plus minus 3 times the signal, mu plus minus 3 times the standard deviation. However, we try to plot in 95% time, but they look really close. So that means there are non-unique solutions. So we presented only mu plus minus standard deviation. Overall, if you look the coefficient of determination and natural tip fall within the monastic criteria, and as expected, both measure observed set and base solution fall within the range of mean plus minus standard deviation. And here are a key summary of this one. Variables, as you see in WI1, there are only three response variables are engaged after grading. But after grading, but in WI8, all response variables engaged except nitrogen stage, which is DB. And we also explore try to explore the parameter range of log likelihood DNA. And here you see in x-axis the time and y-axis log likelihood of each segment, not the whole years. And the bluer the color with negative values, better the predictability is. It means the one set of parameters cannot predict the whole year, all the simulation entire year perfectly. But there are some years which are better than others. In conclusion, we developed a simplified calculation procedure for an agrohydrological model apex grade that includes recently modified grading model. We use a calibrated parameter set within the prescribed range to perform uncertainty analysis, and we add in the normal distribution of hydrologic related parameters, and we studied the watershed processes in grassland with native priority and cropland with annual winter wheat and 1 year of growth under grading operations. And this approach seems to be holistic, and it can reveal non-unique solution to runoff processes. Further, grading operation is more impactful in grassland than in cropland, as you see the differences in the variability in the table. And then the uncertainty analysis is that there is no unique set of parameters that predicts all years considered equally good. But some parameters are good for certain years within a period of simulation. And finding from this work may highlight the need for adaptive grading strategies to allow the sustainability of the crop plant system. Going ahead as a collaborative effort in future, such a holistic approach suggested us that we can utilize this protocol in parameterizing other hydrological models like SWOT, erosion water quality model, and DSAC, and we can use the catalog of this parameter sets may be used for other projects as well as exploring other research questions in the same water sets. And we plan to use this approach in NCAR and MSc related project under the supervision of MSc faculty and ARS scientists, such as runoff project and integration of apex with groundwater models. And the calibrated set may also be useful in studying different climate scenarios, from global climate, global circulation model, and also implied by uncertainty range of parameters. This could be there could be another research avenue using apex model to investigate the temporal dynamics of process-based parameters running individual years as part of climate change study, because we see that the log likelihood graph, there 1 year can be the well, other year not. So that means that's the reason I have insight on that. And then since the current approach rely on normality of parameter distribution, my next step will be we'll be developing the innovative approach to develop heuristic and optimization scheme in the physically based model. Maybe for that, we may like computer grad group or grad student or other researchers to collaborate to advance this matter. And you have a list of references. And I should acknowledge all the scientists and faculty and my colleagues at the units put forward this work. Thank you for your patience and we appreciate your patience.
Okay.
So in one of your slide, you showed a table WRE1 and WRE8 of, and there were several variables that were in, so WRE1 was increasing for like 3 variables, right?
Yeah.
And in another one, it increased, WRE8, it increased for all the variables except nitrogen stress. So why is that case?
Well, it is a bit, but it is a within the parameter range, but maybe, but we have, but even there is a variable, but they are very small. You can see the ranges are very small. And that I mentioned, there are infrequent grading operations and similar kind of agricultural activity. But even there is like a less in the degrees, the degrees are more variable than WREF. That's and then there could be the another is like maybe pesticides and in grassland there are less pesticides and fertilizers, and that could be the reason.
Thank you.
Welcome.
In this crop plan, what you are basing, the crop or with a gas there?
Well, I thank you for this question. In the grassland, there is the forest, and then in the cropland, there is the grain. So.
In cropland? Crop.
It's wheat.
Yeah, wheat and winter.
Wheat,
Wheat and
wheat is
yeah.
allowed to graze.
Yeah, grazing the wheat.
So in grassland, you have native gas.
Yeah,
Is it a C3 gas or a C4 gas?
Forest, yeah.
What is that?
Pardon?
In the grassland, there are C3 and C4 variety, the broad spectrum classification.
Okay.
C3 and C4. Is it a cool season gas or warm season gas?
Grasslands, it's native prairies.
It's a mix.
It's
Mixed
a mix, yeah.
Understood that one, yeah, thank you.
So, yeah. What is it a daily time scale model?
Yeah, this is daily, this kind of daily time scale.
Yeah, it's better to say, what kind of model it is, the one we use, and, what are the crops were simulated. It's like crop is just what radiation with efficiency. Also, people simulate crop, just multiply radiation with the efficiency, you get the yield. So it's better to say these are the processes simulated, and these are the methods, so that one person seeing it, oh, can be due to that method. We can connect.
Yeah.
Okay.
Yes, but we are mostly concentrated on runoff hydrology. That's why we haven't mentioned that. Yeah, we can, thank you for session, we can mention that in that.
And different years, you get different results for the same parameterization. That means the parameters is not optimal.
Yeah.
Yeah. So because sometimes, we call the hill climbing
Yeah.
and, falling in ditch. So it may be falling in ditch and finding an optimum there.
Yes.
So it never climbs the hill
Yeah.
and goes to the other side.
Yes.
So,
But we haven't used that concept, I'm doing this, only normal distribution. So we have used just to discretize the parameter from quantity maximum and minimum. So there is no question of hitting in the climbing and falling because
And
that's what we are to.
And if you get different results for different years, what do you think are the problems? Because we can't use the model.
Yeah.
If you get different results for different years, so you have no confidence in the model. So what can be the problem?
Well, one thing is we need like a yearly data, right? Daily data with runoff, we can generate daily and we can measure, but other like crop yield and other things, maybe that is not possible. Maybe ETG can do, but the crop yield and other parameters we can gather daily sets, So that would be one of the problem we can see.
And there can be a problem of over calibration.
Yeah.
Okay, because when you use, these are methods used in physics.
Yeah.
You measure, this particular surface,
Yeah.
you can measure with the precision. But in agriculture, there can be error like 10 to 30%, error in measurement. Okay, here the measurement is 0.0001.
Yeah.
So that method, when you use in agriculture.
Yeah.
You know what I'm saying?
Yeah.
So there can be overfitting. A lot of problems. We can discuss that.
Okay. Yeah, this is also it's inherited from my PhD research.
Yeah.
I did like that way, and then maybe we can see like because the parameters we cannot measure. What if we can visualize them as in a temporal scale or what it happened? This is my just research question. We can just.
Any other questions? I have a quick one. So go forward some slide,
For what?
forward, yeah. No, oh, it's back. All right, keep going. Yeah, that one, no, go back. What's your last bullet mean? Behavior of grassland and cropland under the same climate?
We haven't talked about, but that means like we studied, we see the different behavior like in grassland, there are more variable and cropland is less variable because there are variability is higher in between mass water balance so between without grazing and with grazing.
Okay, okay.
So that's not.
That's what I thought you were going for, but I was just thinking.
I missed that sentence, sorry for that.
No, you're fine. Any other questions? All right, with that, I will thank Dr. Mahashmaski for speaking.